All right, hey everybody. So today's office hours, I don't think it's going to be a very long one, but happy to take questions as well. So what I want to talk about today is more in like the evaluation of your model. This doesn't just have to be for your final model, but also good to keep track of while you're doing intermediate modeling as well. So mainly what I'm going to be talking about are first of all, the two metrics of R squared and RMSE and how they sort of play their part in picking a final model or deciding whether your model is better or worse than your previous one. And then next I'm going to talk about residuals and how we look at that. So first to start, let's actually take a look at our some of the stuff that we did yesterday. So yesterday we had we basically wrote a function that does our modeling, but I'm not going to talk more about that today. But I just want to talk about a few different results. So actually, let me throw out this one. Okay. I've been getting a bunch of questions saying that like, hey, my R squared is not very good. I think I've seen like R squareds between like the 30% to 60% range, which, as you know, means that your features are only explaining 30 to 60% of the variation in your target variable, which contextually, it really depends on the context, whether that's good or not. And not only that, you also have to look at your RMSE as well. So I do want to talk really quickly about R squared and what that number actually means in terms of, is it a good model or not? So an R squared is literally just a measure of how well that line is fitting your data points. If you remember, it is the ratio of the distance between the points and the line versus a really, really bad model. So if I just quickly annotate over here, let's just say this is our, oh, this is bad drawing. Okay, let's just go with this. Okay, so let's just say I have a bunch of points over here. And if I have my R squared is sort of like a ratio of how well is this line. So let's just say this is our regression line. We're going to calculate all the distance between the points and the line and compare that to our bad baseline model of like comparing it to the mean. So it's just a ratio of how much better is that line versus a flat across line. So it's really a metric of model fit, which is a good thing. Model fitting, like, you know, the fact that your line fits your data points is a good thing, but not the most important thing, because there are two kind of different forces at play here. When you're doing your modeling, as I mentioned before, there is modeling for inference and modeling for predictability. Now, if you have a regression line that fits your data fairly well, there is a chance that, you know, we talked, was it yesterday or we talked last week, I think, about cross-validation and a model sensitivity to data. So let's just say that these X's are our training data. So if these X's are training data, and let me see what other little stamps I have. Okay. And let's just say that I have some test data. It just so happens that my test data is here in this realm. And it just so happens that my random chain test split it this way. Then obviously there's some overfitting going on, right? There's some overfitting where this blue line is overfitting to the red X's versus the question marks. So because of that, you always want to look at two things. Model fit is not the most important thing. So if you don't have a great R squared, not the worst. Instead, what you also should be looking at is your root mean squared error, which I have over here. Root mean squared error will tell you how good at predicting your model is, because this number is in the units of your dependent variable. So here, miles per gallon, so I guess miles. So here is just saying that for my train set, my model on average predicts about 4.138 miles off, and then my test set 4.52. Now there's a bunch of other things, not a bunch, but there's some other things to think about when you're looking at RMSE. If these two numbers diverge a lot, it's a very, very strong sign of overfitting, because if you have your blue line here overfitting to your train set, which are the red X's, you have a smaller error. And if I were to look at the question marks over here, the error here is going to be overall greater on average, because they're all down here. I know it's not the not the best diagram, but I hope it alleviates some fear about not having a good R-squared, because that's not the most important thing. I would be more worried, actually. I mean, again, it does depend on context, but I would be more worried if my RMSE was just awful in comparison to your baseline RMSE, of course. So that's like my quick spiel about metrics. That's why R-squared is not the only thing that you want to look at. You definitely want to look at RMSE, and I do expect to see at least some RMSE value, especially for your final model, just to see how off your predictions are on average. But yeah, any questions about these metrics? RMSE and R-squared are the main two that you look at. Questions about this? Okay, cool. So moral of the story, high R-squared is not the most important thing. Actually, if your R-squared is too high, actually, let me just draw another diagram again. Actually, can I undo that, delete? Okay, if your R-squared is too high, that just means that, first of all, like all of your data points are like this along the line. This will give you a very, very high R-squared. But again, you have the problem of, let's say I did a train test split, and these question marks on my test set. First of all, your test R-squared is going to be much lower, and your train and test RMSEs are going to diverge as well. So things to keep track of. Usually, if you have like a very high R-squared of like 0.95 or and above, some people like it makes it you're naturally skeptical when you have a very, very high R-squared. Okay. The next thing I wanted to talk about, and pretty much the other thing I wanted to talk about today, is residual plots, because residual plots I feel like we didn't get very much into. So let me just collapse these sections real quick.
Sorry, real quick.
Oh,
if
yeah.
you end up getting a smaller RMSE in your test, that's usually a good sign.
That I would say is not a good sign. I mean, it's not bad. It's not bad. Typically, if you have a smaller RMSE in your test set, it just so happens that your test data points are the ones that are closer to the line. It actually pretty much always your test results are not as good as your train results, which makes sense. But it just so happens that if your test set is within the domain of your train set, which means that if your test data points are not a lot of outliers, or not like, if it doesn't include, mainly if it doesn't include extreme values or outliers, then yeah, there is a chance that your test data can be better.
I mean, would that mean that it would be better to rerun a train test split again to get a different subsection to make sure?
I would say if you're seeing that your test metrics are too high, if anything, I would do a cross validation rather than redoing.
My test metrics are lower than the train data.
And by metrics, you mean RMSE?
Yes, yeah, but the RMSE is lower.
Yeah, usually if that's the case, I would just check a cross validation to make sure that, but actually, yeah, it's not a bad thing. It's not a bad thing. I wouldn't be worried if your test metrics are better.
Okay, thank you.
Good to cross validation and check anyways. Okay, let's see, we don't need to talk about scripts. Okay, so let's do some assumption checking. And we talked about 4 assumptions so far in total: linearity and multicollinearity that you do during your EDA. And the other 2 of normality and homoscedasticity, you do after you build your model. So let's take a look at that. And I'm gonna demonstrate this using residuals with stats models and scikit-learn. You don't have to do both, just depending on which one fits better into your workflow. All right, so to start, same regression we're gonna use, just this simple one, miles per gallon and 4 continuous features. One thing that stats models has is it actually stores all the residuals for you. So if you take a look at model.resid, and you might have seen this, and I think the QQ plot has this as well, you might see, well, if you see this actually outputs the actual minus predicted values for whatever you trained your model on. So if you, for this case, I didn't do a train test split here. So therefore, the number of rows in my resid matches my input. So these inputs have 392 observations. So therefore I have 392 residuals. This is exactly the same as doing model.predict x and then model.predict x. Wait, sorry, other way around. So it'll be y minus model predict x. Oops, that's not what I wanted to do. Okay, never mind. It'll just be this minus the actual value. So if I have my y over here, there we go. Let me think if I do this, dot flatten, let me just quickly do this. So, okay, here we go. So I have this value minus this value. Here we go. This matches this. The reason why I had to do flatten was because my y was in a data frame. If I do dot values, it's in a 2D array, as you can see. And I did dot flatten, which is a NumPy thing to make it into a 1D array so I could directly compare it to model.predict. So anyways, the residuals are the same as actual minus predicted. Those are residuals. And so in our next few, we're going to talk through some visualizations that are going to show you how you can make use of residuals and how that kind of relates to RMSE as well. So RMSE is actually a root mean squared of these residuals. So if you take the model.residuals and I guess you square it, and then after you square it, you take the, you divide it by what, 392, divide it by 392, and then you take the square root of this. Oh wait, and then you want to sum it and then, does that work? Cool, nice. And then we take the square root, 5. That is our root mean squared error. Just so you know, your residuals are directly related to your root mean squared error. However, your root mean squared error is an aggregated form of your residuals. You can imagine that like if I have one super outlier in my test set, it can really blow up my RMSE. So it's important to check out the distribution of your residuals. And that's where our assumption checks come in, because the assumptions are that our residuals are normally distributed, first of all, and also that our residuals are homoscedastic. So to check for the normality of residuals, QQplot, that one is a built-in function that's pretty easy to use. Also, you can do model.resid, and I think you can, let's see if I remember how to do this. I can do a histogram of this, plt.hist. Okay, I have to import this first. Here we go. So it looks okay, fairly normal, cool. But I also want to show you all residual plots. So here I have some code. I have 2 different residual plots, and I want to outline what these show us. Okay, so here there's 2 ways that you can do residual plots. First, you have this one on the left, and this one on the left has our actual miles per gallon values on the x-axis and their associated residual on the y-axis. And you can see that there's this horizontal line at 0, and 0 just means perfect prediction. So as you can see, the points up here, for example, the residuals are positive, which means that the actual minus predicted goes up to like a 15-mile error. So what you can see, or what you can gain from this plot, is that from values, let me just annotate real quick, values around this range of here are being under predicted, because the actual minus predicted, you have a residual of like 0 through 15. So there's a lot of under prediction going on here. Same for over here. All of these points are being over predicted because the residual is negative. And you can see that across the range of miles per gallon, there is no consistency. So from this graph, you can see that it is not homoscedastic. If it was homoscedastic, you would be seeing a residual plot that looks a lot more even. Oops, didn't mean to do that one up there, but one that's more even across the range of miles per gallon values. Now that is homoscedastic. This unequal variance is not homoscedastic. It's actually heteroscedastic, because you can see that the variance kind of changes. Like up here, the variance is around this range here. In this range, the variance is like this. And over here, your variance is like way up here. So it does not have a consistent variance. So this actually does not fulfill our assumptions. And you can see that as our miles per gallon reaches the 30 to 50 miles per gallon range, our model tends to underpredict, which is inconsistent modeling. So questions about interpreting this graph on the left? Okay, cool. So now this graph on the right, very similar information, but this is plotting our actual miles per gallon versus our predicted miles per gallon. And so instead of having a horizontal line across, I actually have this red diagonal line. And this red diagonal line is basically a y equals to x line, if you're familiar with math and functions. But this line is basically at where these values are equal. So anything that lies on the line is a good prediction, is a perfect prediction. The further away from the line you are, the more off your prediction is. So you can see here, and this actually gives you very, very similar information. You can see here on this end from like the 30 to 45 range, the actual values are down here, but your predictions are down here. Sorry, your predictions are down here where your actual values are there. And so there's a discrepancy of about this much when you get to the higher ranges. So basically, again, you can see that one, it is not homoscedastic, but also that it is not consistent at predicting. Because what you want is you want seemingly random errors. And the fact that in this range, the errors are almost always too high, or you're almost always under predicting, I should say. There's some inconsistency there. So these are good graphs. Either one, I think they pretty much show you the same information, or in this case, I have both. Either one can show you how well your model is doing at predicting. Now, this connects with your RMSE because your RMSE is an aggregated version of these errors. So like you can sort of infer that, let's say I have an error value that's all the way down here. Let's say I have a data point that's down here. There's an error of this much, and this can really blow up the RMSE. So if you're seeing RMSEs that are higher than you expect through a residual plot, maybe you can find out what your outliers are. Maybe you have outliers on like the actual axis. Maybe that's even like some data points that you should be taking out. Or if you see that over the range of housing prices, your residual plots, instead of looking like that, and let me just do a quick fake line over here. So let's just say this is our 0 line. Let's just say our residuals look something like this as an example. That just means that you are over predicting very much here, under predicting very much here. Maybe make the scope of your model smaller. So maybe you can build a model that only focuses on this range of houses, so on and so forth. Different things that you can use to evaluate your model. And this is using stats models model output. So as you can see here, this plot is literally, sorry, before that, going into here I just modeled on X and Y. So therefore, in my plotting, I have Y on the X-axis for both actual miles per gallon. And here I'm using model.resid, and here I'm using the predictions out of stats models as well. Questions about this before I move on to doing this within scikit-learn? All right, so scikit-learn, kind of similar, but now with scikit-learn, I do want to show what this is like with train test split. So with scikit-learn here, let's just say I run the same models, but I have my train test split. I have my train R squared, test R squared, train RMSE, test RMSE. Dimitri was saying earlier that my test RMSE in this case is also smaller than my train RMSE, which is not a bad thing. But one thing that you can also do to check out to see whether anything weird is going on over there is do the same thing. Now, the only difference between these plots and the one above is that I'm just using different colors for the training test set. So these, the model is fitted on the blue data points and tested on the orange data points. So you can see here, one reason why my train RMSE could be larger than my test RMSE, just based on how this train test split was done, you can see that there are a lot more of these higher miles per gallon that made it into our train set, but not in our test set. And so therefore, maybe just the overall error is less because of that. Yes, there's like one outlier down here, but I think overall these being further away have a greater impact. Like same with over here. You see that this group is the one that is probably causing a lot of the error in our model. And there are a lot more blue data points than our orange data points. So exactly the same graphs as above. This one now just discerns between our train set and our test set. Just so you can see, what the error, I think it's good to, RMSE is an aggregated version of our residuals, but sometimes it is important to look at residuals because that shows you if there are any like systematic errors. Systematic errors meaning that like, you know, this area is just consistently under predicting for some reason and might compel you to change something about your model. But yeah, I'm a big fan of these graphs, as you can probably tell. I will push this notebook up to your study group repo right after this so that you can feel free to use this code if you'd like. But yeah, any questions about this? Awesome. I know you are all underway with your models. What's that sentence? You're all working on your models right now. So does anyone have any questions about something that they're working on that I can help with? In 24 hours, you'll be presenting your projects, and yeah, happy to answer any questions. I'll be online on Slack all of today and the rest of the night as well. So yeah, I'll put a presentation order up tomorrow morning too. Cool. Well, if there are no other questions, I'm going to call it for the day. So going once, going twice. Feel free to Slack me with anything. I'll put a presentation order up. Now that your phase 2 projects are finishing up, I think a good idea for the break is to just get a head start on your second blog post. I'm going to make I'll put a note about that on your homeroom as well. But yeah, if there are any questions, you can Slack me for the rest of the day. I'm seeing a bunch of you for one-on-ones later as well. So yeah. All right. If there's nothing else, I will see you all tomorrow for your presentations. I'm so excited to see what y'all come up with. And yeah, have a great rest of your day, everybody. Bye.